This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, everybody, welcome to Physics 1, Lecture 15. Semester's moving along nicely. Today we're going to continue on with our lectures on rotational motion. What we're going to focus on today is translation, rotation, and rolling. So in our last lecture, we discussed the topics of rotational inertia and rotational kinetic energy. We had a look at the parallel axis theorem, and we discussed analogies connecting linear and rotational motion. Our lecture today is going to continue on in that manner. Now, from the last lecture, at the very end, we related our power-work relationship, knowing that power is the change in work over time, which itself is a change in energy over time. So we looked at that in terms of tau times the rotational velocity. And of course, we gave a full list of all the analogies for looking at linear versus rotational motion. You can see that here in table 10.3. We see how everything translates across. So take some time to get to know how that works for you. We looked at our relationship with torque, which is our tau, power, kinetic energy. So just get an idea of how these translate across, because what we're going to do today is focus on how we can make that apply. And we're going to look at something, a very special case, which might initially seem counterintuitive. And that's if you see something rolling on a surface, you'll notice that the top of that object seems to be moving faster than the bottom of the object. And that might seem strange. So if you're looking at, for example, a bicycle wheel that's moving and you take a snapshot of it, you're going to see that the spokes in the bicycle at the bottom seem still. The ones at the top are very blurry because they're moving very quickly. You can see that illustrated in figure 11.12 here, where if you've got a light on this disc, even though the whole thing is moving at the same velocity with the center of mass, the top seems to be moving faster than the bottom. And what we're going to do is we're going to explain why that works here. So for rolling objects, we're going to only consider, for simplicity, right now, objects that roll smoothly, which means they're not slipping. The center of mass of the object moves in a straight line parallel to the surface. The object rotates around the center of mass as it moves. So the center of mass isn't going to be going up or down. It's going to be moving purely in that x direction, and that's going to be the center of mass. That's going to be the overall velocity of the system. Now, we looked at this early on, a couple lectures ago. The rotational motion is going to be defined as the radius of that object times theta, which is measured in radians. That's the rotational motion on the outside of that object. And the speed of that object, the speed there, is going to be equal to the rotational velocity times the radius of the object. Equations 11.1 and 11.2. These are things we've discussed before. So what we're going to look at when it comes to, let's say, a bicycle wheel moving in space, there's two components of this we have to examine. One is purely rotational. So this one is just about the center of mass not moving. It's just the object spinning at the outer edges. So we can say that the velocity at the top is going to be moving in the positive direction relative to the center of mass, and the bottom is going to be moving in the opposite direction. So the lower point in contact with the surface is stationary and has a velocity equal in magnitude but opposite direction to the upper point. So that makes sense. Those 2 points are exactly the same. As it rotates around, the top part's going to be moving in this direction, bottom part's moving in this direction. Their magnitude is the same, but they're opposite in direction. And of course, this is dependent on the angular velocity of the wheel as it turns at the point 0, which is the center of mass. But we have to add that to the pure translation, the linear motion of that object as it's moving in space. So in that case, all three of those components are moving with the same speed in the same direction. because the wheel is moving in the positive x direction. So for the center of mass, for the point on the ground, or for the point at the top of the wheel, all of them are going to be moving with that velocity. And they're all going to be equal in magnitude and equal in direction. So what happens when we add these together? Well, if we look at the center one here it's 0, it's not moving, and here it's not moving with this velocity at the center of mass. So the total result for the center is going to be v com, v center of mass. For the top part, it's going to be moving in this direction, and then the whole system moves in that same direction. So it's actually going to be 2 times that value, whereas at the bottom, this is moving in the opposite direction. So this plus this value cancel each other out. And what we get in this, is that the bottom cancels out, so it's actually at rest here. The middle part is moving with its center of mass velocity to the right. The top part is moving with twice that center of mass velocity, which means that this top part is moving twice as fast as the middle, which is, the bottom part is not moving at all. So that's why it'll seem like a point on the bottom of that wheel is solid. It's not moving, but the top part is moving very quickly. It's actually moving twice the velocity at the center of mass. So just to reiterate this, the velocity of the point at the top of the disk is the vector sum of the velocity of the surface relative to the center of mass and the velocity of the center of mass relative to the observer. The velocity of the point in contact with the surface must be 0 because it's not slipping. So now what we can do is we can do another way of combining this. We can combine their relative kinetic energies. We can combine the translational kinetic energy and the rotational kinetic energy. So the rotational kinetic energy is simply the mass of the system times that center of mass velocity squared divided by 2, 1/2 mv squared. The kinetic energy translational, as we've looked at before, we remember for our equations before, is the moment of inertia of the center of mass times the angular velocity squared divided by 2. That's simply going back to our equations here for kinetic energy. So, reiterating our point, a rolling object has 2 types of kinetic energy. There's a rotational kinetic energy as it rotates around the center of mass, and the translational kinetic energy as it moves across in the x direction through space relative to its center of mass. So if a wheel accelerates, its angular speed changes. Therefore, a force must act to prevent it from slipping. Well, what's going to prevent it from slipping? So we can write our equation, or the acceleration of the center of mass of the object is going to be the rotational acceleration times the radius. And that's again something we got from our previous table. So let's have a look at this. Let's take a rolling object on a ramp. And it's going to be sliding, or not sliding, it's going to be rolling down. So, all we've done here is we've taken our nice simple system, we've tilted it off at an angle, which means we have to use our trig functions, our Pythagorean theorem. But the main thing to relate here is that as it rolls down, to prevent it from slipping, you have to have a frictional force. That's that static frictional force. Otherwise, if it were the kinetic frictional force, it'd be the friction as it's moving, but it's not moving because it's not slipping. So therefore, as there's a force, which is, put our free body diagram in, let's look at it here. There's our force of gravity pulling straight down on the object. There's our normal force, which is always perpendicular to the plane on which it's resting. Therefore, this value here of that normal force, opposite that, is going to be Fg cosine theta. And then this component here, which we're just showing up here, is Fg sine theta. So Fg sine theta is pulling it down the ramp, and our frictional, or our static frictional force is preventing it from sliding. Now what this frictional force does here is it puts a torque on the system because there's that force times the distance from the center of mass, which is the radius. So it's actually preventing it from slipping by adding a torque onto it. So we can see here that the normal force and the force of gravity times cosine of theta, those just balance out, of course. So the forces, the torque due to the frictional force, static frictional force, determines the angular acceleration down the center of mass, or around the center of mass. So therefore our forces of Fg sine theta, which is the force in this direction, and the frictional static force in the opposite direction determine the linear acceleration down the ramp itself. So, we go back to all of our different moments of inertia for things that roll. And you're going to notice a common relationship for all of these. Very simply put, there's your mass times that distance squared, in this case the r, and in front of that it's going to be some value. If you look at all of these, they follow the same basic principle. There's some sort of value in front of that. Whether it's here, it's 2/3 mr squared, it's 1/2 mr squared, it's 2/5 mr squared, 1/12 ml squared, it's that distance squared. This little value here we can think of as c. So we can write the moment of inertia as I, our moment of inertia, is equal to c times m, that distance squared. So m is the mass of the system, r is whatever that distance is, whether it's a length or a radius. And that c at the beginning tells us a bit about the geometry of the object itself. So we can write this c is going to be different for the different types of objects we're going to be looking at. So for point particle, it's simply 0. But because of a point particle, it's not rotating because it's a point. So it's going to be 0. And we can see our different values. So 2/5 is for a sphere. So as we have here, the sphere right here. 2/5. For a hoop, it's 1. So we can see those different values in here. So we're going to look at something rolling down. Is it going to be a sphere, like a bowling ball? Is it going to be a loop? Whatever it's going to be. We're just looking at these terms of c. So anything can be accommodated for rolling down just by adjusting that value of c. So point particles sliding with no friction behave similarly to a very small particle rolling with friction, because there's no accumulation of rotational motion if the moment of inertia is very small. And all we're going, this is something we've discussed before. So if the moment of inertia is extremely small, it's going to act like a particle sliding with no friction. So what we're going to do here is we're going to look at our conservation of energy. And we're going to have our two values of the kinetic energy is going to be equal to our potential energy. So remember, conservation of energy. The potential energy plus kinetic energy is equal to 0. In this case, the potential energy is going to be equal to the final kinetic energy. So mgh, m is the mass of the system, h is that distance, that height of the ramp itself, and of course g is simply gravity. Now we're going to look at our two components of that kinetic energy. We have our rotational kinetic energy and that sort of translational kinetic energy. We have to add those components to get our total kinetic energy, which is going to be equal to our potential energy. So what we can do in here is we can do some mathematical substitution. So in this case here, for the translational kinetic energy, where m is the mass of the system, we can say that this v, this velocity, the speed of the center of mass is going to be equal to our angular velocity times r. And this goes back to the table we showed you before when we translate things across. So in this case, we simply plug this value into our equation. And here, that value squared, we're just plugging and chugging as we go along. So we have our value for the c in here. So I is equal to c, some value depending on the object itself, times mr squared. So here is c mr squared. 1/2 is the same as before, but now in this case, we simply solved for our rotational velocity. So r moves down, and that plugs into the equation here. It's squared as before, or plus 1/2 mv squared. So now we have the same values. We have this rotational speed in here on both sides. So, well, we simply add these two together. So this plus this gives us this part here, and this equals still to mgh. So again, have your pad and your pen or your pencil out and be working through the mathematics as we go along. So it's kind of difficult to show you. I can't really work it out. That's why I've got the PowerPoint here for you. So here we have this second half of the equation. Our combined kinetic energy is equal to our potential energy. And now all we need to do here is solve for our speed of our center of mass. So we see the masses cancel out. The 2 moves up here. So it's 2gh divided by 1 plus c, and then we take the root of that. Therefore, our speed of the center of mass is given by 2gh over 1 plus c root of. So this tells us that our result is independent of the mass and of the radius. It only depends on the geometry of the object through our value of c. And remember that c is going to depend on the geometry of the object. So from linear kinematics with constant acceleration, we go back to earlier in the semester when we derived our kinematic equations. One of them talked about our velocity with respect to position. It was independent of time, just respect to position. And that equation, as you'll remember, was the square root of our final velocity minus the square root of our initial velocity was equal to 2 times acceleration times that change in position. We're not worried about the initial velocity now, so we simply have the speed of our system, that velocity of our system, is equal to 2 times the acceleration of the system times whatever that change in distance is going to be. In the case of this thing rolling, it's going to be h divided by sine squared. That simply goes back here. We have h, that distance, times sine theta. So with this, now we start plugging these values in. Again, have your pen and paper, be working through this as we're going along. So we substitute, we put h over sine theta in place of this here, and then we plug these, or we solve for our acceleration for the center of mass. So the velocity squared divided by 2 divided by that change in distance. Now we plug our values in for this that we derived before from in here. 2gh over 1 plus c, we put that in here. That's square root. This is squared, so those cancel out. We're just plugging and cranking things out. And then we get our final answer is g times sine theta over 1 plus c. So if that geometric component didn't matter, it'd simply be g sine theta. But that geometric component does matter, that's why it gets added here. So a frictionless sliding point has an acceleration. The particle is equal to g sine theta. So therefore we can see that our acceleration of the center of mass is equal to the acceleration of the particle divided by 1 plus c. And again, c is something above 0. It has some kind of value for that moment of inertia. Otherwise, it'd simply be the same. So if it's a little bit confusing, go back with your pen and paper. I cannot emphasize this enough. Be working through that as we're going through these slides. So now we can compare the acceleration of a frictionless particle with that of an object with non-zero moment of inertia. So it has some moment of inertia. Imagine that we release a point particle, a sphere, and a hoop. They all have the same mass at the top of that inclined plane with some height, with some friction. For any value of theta, the point particle will reach the bottom of the plane first. For the other objects, the sphere will have the greatest acceleration and the hoop will have the least acceleration. And the reason for that is, going back here, The sphere, it's that value of c. Remember, it's 1 for here and 2/5 for the sphere. So if you're not sure why, go back to this equation, cranking your numbers for that value of c. So here the acceleration, the hoop is going to be 1, but for that other one it's 2/5. So you're going to see how that's going to change. Sorry. The hoop converts more potential energy into rotational kinetic energy than in translational energy. So, again, you can go back, you can put the numbers in for these values, and you can see why that's the case. So this hoop converting more potential energy into rotational kinetic energy than translational energy is why we have our automatic braking system in cars, or anti-lock brakes, ABS. So what the ABS system does is it tries to prevent slipping. So what it tries to do is match the velocity of the wheel with the velocity of the ground. So the ABS senses the wheel's speed and releases short bursts of the brakes, so the tire speed, which is that hoop essentially, matches the speed of the road. Now, experienced drivers can practice this by just sort of slowly tapping the brakes. But what the anti-lock braking system does, as many of you already know, is if you're driving and this happens and you slam on the brakes, instead of just stopping it where you're going to slide, the system just does short bursts of it so you don't slide. Because sliding, once you kick that coefficient of friction in, if you've driven in snow or water, you can hydroplane or slide in the ice. So that's why it's important to have that slow pulsation to slow it down to match the wheel speed with the ground speed, or else you just slide and then you can get into a pretty serious wreck. I'll post a video of this anti-lock braking system in slow motion to show you. This is somebody driving in snow and ice. I'll post that in underneath this video link. So let's look at a different example. Let's look at a yo-yo. So we can think of this as a wheel rolling downhill. Yo-yos are a very interesting sort of case for looking at rotational motion. So let's compare the acceleration of a frictionless particle with that of an object with a non-zero moment of inertia. So going back to exactly what we did before, it's got some moment of inertia, some sort of geometric effect, therefore that acceleration is going to be slightly higher than the acceleration of the center of mass. So we can apply this to the case of a yo-yo, provided that we're careful about identifying a couple things. We have to think about this system, and we have to make a couple of base assumptions to simplify it a bit. We have to look at the force that keeps the axle of the yo-yo rolling along the string, and we have the effective value of c that is relevant to this problem. So I think everybody knows how a yo-yo works, but there's basically two cylinders. There's the cylinder in the center for which the string is wrapped around, and then there's the outside of the yo-yo itself. And that outside of the yo-yo creates a greater angular momentum, which when it accelerates, increases the centripetal force. We're not going to go into all that now, but we want to give an idea of a yo-yo for rotational motion. As the yo-yo moves down the string, it loses potential energy, mgh, because it was here. As it's moving down, it's losing potential energy, but it gains rotational energy and translational energy in kinetic form. So to find the linear acceleration of a yo-yo accelerating down the string, we have to imagine that it's rolling down a ramp of 90 degrees. It rolls on an axle instead of its outer surface. So in this case, instead of it rolling down the ramp on the outer part of the yo-yo, it's actually like it's rolling down the ramp on the inner cylinder of that. And it's actually slowed down by the tension rather than the friction. So as the string pulling up, as the system is going down, there's a force down, mg, and there's a force going back up. That's the tension that's counteracting that force of gravity. So it's not so much in this case friction, it's just that tension as it's rolling down. So we're going to assume that the yo-yo consists of two discs of a total mass m and a total radius r. The central cylinder is of negligible mass. Again, we're having to just sort of simplify a little bit. So that central cylinder has no mass, but it does have a radius r naught. So the moment of inertia of the disk is 1/2 mr squared. And that goes back to our equation, or our value for the moment of inertia that we looked at before. It doesn't matter that there are two disks because only the total mass counts. So I'm going to see if we can pop back real quick and have a look at that. Where is it? Yes. So right here, 1/2 mass times the radius squared. So that's where that comes from for the 1/2. In terms of r naught, the radius of the small disk in the center, the moment of inertia can be written as such. So what we're going to do here is an interesting little trick. So we've got the moment of inertia is equal to 1/2 mr squared, where mass is the total mass of the system squared, total mass of the system times the radius of the whole yo-yo squared. And what we're going to do in here is a little trick. We're going to multiply it by 1. Now you might remember we did a similar trick when we were deriving our kinematic equations, and we had to calculate that equation for velocity with respect to position instead of velocity with respect to time. We simply multiplied it by dx over dx. We're going to use a similar kind of a technique here, where we're going to multiply it by r naught squared over r naught squared. It's just 1. But what we do is we write that as the ratio of r squared over r naught squared times r naught squared. So these two cancel out. But what we're going to do is a bit of substitution in this equation. We're going to show that, well, if mr squared, that's equal to the moment of inertia, this 1/2 here, this is our geometric component, or our c. And in this case, we can take this ratio here and move that as part of c. So we're wanting to get this in terms of our r naught with the moment of inertia of the whole system. So this component here, we're moving that with the 1/2. That's our c. So then c times m times r naught squared. So I hope that makes sense. We've just done a little trick there to put it in terms of, sorry, my mouse is very sensitive and it will jump slides if I do this, if I even touch it very slightly. So what we've done here is just put this in terms of r naught instead of r by multiplying it by this value. So c is equal to 1/2 times the ratio squared, as we've got here. Therefore, that is c times mass times r naught squared. Now we can replace those values going back to our equation 1110, where we had a center of mass is equal to acceleration of the system divided by 1 plus c. And what we've done here, what this whole messy looking thing is we've just substituted these values in, because I is equal to this. And we know that the system, going back here, we've just substituted those factors into it. So it might look a little bit messy now, but because the yo-yo was moving down, that gravity is going to be there. That's the gravity of the system otherwise. So the acceleration of the system would normally be gravity just going straight down. But there is that factor in there. The negative sign shows that it's actually moving down. That's why the negative sign is there. Because that particle is, that whole system is moving downwards. So we want to calculate the acceleration of the yo-yo. We can put in some initial values of this to see what kind of answer we get. So, yes, my cat. So again, have your pad and paper and be working through this as we go. We've derived the equations. We've shown that the acceleration of the system is g over 1 plus and that value of c. So we're going to put some values in there. Let's say the mass of the yo-yo is 150 grams, that initial radius of the inside disk is 3 millimeters, and we know what our moment of inertia is. So if we convert this, of course, we need to remember to convert this into our standard SI units. We can get our answer as 3 times 10 to the negative 5 kilograms per meter squared, or kilograms meter squared. And we know that the acceleration of this system is 9.8 meters per second squared, g, divided by these numbers we pop in here. So we can see the acceleration of the yo-yo is going to be much less than 9.8 going down because of the factors involved in the geometry of the yo-yo itself. So the yo-yo part, it might seem a little confusing. Just go back with the video with your pad and paper, and we've worked through it step by step. So as a bit of a summary of what we've looked at today, we've looked at the velocity, the speed at the center of mass is relative to our angular velocity times the radius. We've looked at our kinetic energy, the total kinetic energy being the rotational and the translational kinetic energies, and the acceleration of the system as being the angular acceleration times the radius, the distance. So we just touching on things we've looked at before, and we're going to look at the next one. We looked at our relationship between torque and our second law of angular momentum. So again, work through the problems in the book. Make sure you read the book because it's going to go into some detail that we didn't cover in the lecture. Be sure you're going through and doing as many of those questions and problems as possible, and ensure that you are, if you need some extra help, on the link I've provided a link that takes you to all the fully worked out solutions in the book. So make sure you're doing as many of those as possible. I'm going to repeat this in every lecture, everywhere that I can. Work on as many of the questions and as many of the problems as you can. The more of those you do, the better prepared you're going to be for the test, but more importantly, the better you're going to understand the physics. Because at the end of the day, it isn't just about whether or not you can pass the test. You need to understand the physics, because whatever you're studying is going to apply these principles, it's going to apply the physics, and you have to know how it works. Okay, see you guys next time.